Hello. In this video I'm going to go over the SHM problems that we did in class on Friday. I'm going to review the solutions to those and then also go over the review problems 1, 3, and 4. Review problem number 2 will not be on the quiz on Monday. Alright, so let's start by heading over to this question right over here. So on your quiz on Monday, I'm very likely to ask you about the magnitude and direction of either displacement, let's say magnitude and direction of delta x, velocity, or acceleration. I want you to be able to tell me what the magnitude and direction of displacement, velocity, and acceleration are based off of a velocity versus, or based off of a displacement versus time graph. And so to go over these ideas, what I'll do is go over the solutions to the problems that we did in class. At which point or points is the acceleration positive? Wherever the graph is concave up is where the velocity is going to be positive and increasing, where the velocity is negative and decreasing. And for both of those situations, the acceleration will be positive. Justifying this with concavity is not enough. We need to be able to describe the physical or the physics concepts that mean that the acceleration is going to be positive. And so if we talk about the rate of change of displacement, that is velocity, you can see the rate of change is negative and decreasing, right? And here the rate of change is positive and increasing throughout this area. Okay, so at which point or points does the car have zero velocity but non-zero net force? The velocity is going to be zero as the object switches direction. So at its maximum amplitudes, it's going to have some non-zero net force, right? Because if FSP is equal to negative kx, as long as there's some x, there's going to be some force. And at A and E, it's going to have a maximum of the FSP. And the velocity is going to be zero because it's going to go all the way to the outside and now switch directions, and then go all the way to the inside and switch directions. And momentarily on either side, at maximum.
Now, which point or points is the net force on the car equal to zero? FSP is equal to negative k times x. As long as x is equal to zero, the force is going to be equal to zero, and the acceleration will be equal to zero. The only places that this will occur is where x is equal to zero, so C and G. Displacement, zero. Which point or points are the acceleration, velocity, and displacement all positive? None, because the acceleration and displacement will always oppose each other. Take note, on this curve right over here, and this is an example of, this is an attribute of simple harmonic motion. Wherever the displacement is negative, the graph is going to be concave up. Wherever the displacement is positive, the graph is going to be concave down. That's the relationship between concavity and displacement. And the acceleration, and that is a feature of simple harmonic motion. The acceleration will always be opposite of the displacement. Alright, at which point or points is the acceleration non-zero and opposite in sign to the position? A, B, D, E, F, and H. This is because at every point where it's accelerating, the acceleration will be non-zero, and it will always be opposite in sign to the position. This is the same as the previous question. Wherever there is acceleration, it's going to oppose displacement or position. Now, at which point or points is the velocity non-zero and opposite in sign to the acceleration? Velocity is non-zero and opposite in sign to the acceleration. Whenever the velocity and acceleration are in opposite directions, the object is going to be slowing down. And so the only places where it's slowing down on this graph are D and H. F is speeding up, and B is speeding up. And then C, there's no acceleration. Okay. Now, the second thing that I'm going to ask you to do on your quiz tomorrow is be able to draw energy bar charts for a simple harmonic oscillator. And so I'll go over this example that we did in class, but also go over example 3 for the SHM review problems, which also is very similar to this. Okay, so when we're asked to draw an draw an energy bar chart for an oscillating mass and spring displacement time graph, we basically just have to identify where is its max potential, where is its max kinetic, right? And so at point A, when it's at a maximum distance away from the displacement, ESP is equal to 1/2 kx squared. Energy is a scalar. Kinetic energy is a scalar. potential energy is a scalar. Whenever you have a quantity that's squared, it's going to be a scalar. So if we're looking at the displacement here, wherever the displacement is going to be at a maximum is where we're going to have a maximum potential energy. So here for A, you have a max displacement at time 2 and a max displacement at time 6. So point A and point E are going to have maximum potential energy because the displacement is at a maximum. And if it's at a maximum potential energy, then there's going to be no kinetic energy. So let's give it, let's figure out if we can, the total initial energy is 12 joules, and so let's say 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's say 1, 2, 3, 4, 5, 6. Let's say each one of these is 2 joules. 2, 4, 6, 8, 9, 10, 11, 12. 2, 4, 6, 8, 9, 10, 11, 12. Cool. All right. So at point A and point E, it's going to have maximum potential energy. So we'll draw that in over here. Cool. Draw this in on the other side too. Maximum potential. Okay. Now, we know something about point C. We know that here, the displacement is actually 0, and so there's no spring potential energy. So if there's no spring potential energy, we know that all of the energy has to be in kinetic. So on the other hand, we can do kinetic energy. We can show is at max, position C. Cool. Now B and D are pretty interesting because we don't know how exactly the potential energy splits. One way we can figure this out is by looking at the formula over here. So we know the spring potential energy depends on displacement, but we don't know the spring constant. That's fine. Let's solve. We have two different displacements here. Displacement at position, or we have a displacement here, I should say. The displacement at position B is 2 centimeters, and we know the displacement at position A is 4 centimeters. Okay. So at half of the displacement, what happens to the potential energy? Let's see. If x is equal to 4, then we know that we have 1 times 16k, we have around 8k of potential energy. Now when x is equal to 2, we have around 1, 2 times 4 times k, we have 2k. No, not the video game. 2k potential energy. So when the displacement is half of the max amplitude, we know that we have a fourth of the total spring potential energy because of this squared. This squared right there. So displacement's 4 squared 16 divided by 2, 8. Displacement's 2, 4 divided by 2 is 2. We know that we have a quarter of the potential energy. So if we have a quarter of the potential energy, we'll have 3 joules. Ooh, that's a little bit grosser to draw. But 3 joules right there. Then we'll draw 9 joules. 2, 4, 6, 8, 9. Right, because this is 8k and this is 2k. We have a quarter of that. And then at point Z, it's the same thing because we'll have negative 2 squared. So we'll have 2k. So once again, we'll have a quarter of the spring potential. We look at the kinetic energy.
At the maximum, or at the equilibrium position, the kinetic energy is going to be at a maximum, and as the kinetic energy gets further and further away from the equilibrium position, it decreases in a quadratic by a quadratic function. So let's see. So the rules for figuring out the energy bar chart is first identify PE and KE max. And then
determine points in between using formulas. In this case, we use P is equal to 1/2 kx squared, PESP. Okay? Alright, now time to get to review problems. Let's take a look at these. Okay, so just to reiterate for your quiz, I want you to be able to do two things. I want you to be able to determine the sign of displacement, velocity, acceleration, or force from a sketch of an object in simple harmonic motion. And I want you to also be able to sketch energy bar charts for an object in simple harmonic motion. This is SHM 3, and this is SHM 4. Number 2, of these problems you won't have to do. It requires calc. We're not going to go into how to do it. I'll play a video of McNulty solving a problem because he's a calc god. Shout out to the GOAT. Alright, you have a ball bearing in a hemispheric bowl. You let the ball roll down from the top of the bowl. It moves up and down the ball as well for some time. Assume no losses from non-conservative forces such as friction. Is this SHM? Explain why or why not. A bowl looks kind of like this. And we have a ball bearing. A ball bearing is a little hoop that has balls that kind of sit inside of it. Now the ball bearing is going to be let go from the top of the bowl, and it rolls down, up and down, up and down, up and down, up and down. Okay. Now, if it does not lose any energy due to friction, is it simple harmonic motion? Well, it is periodic. Let's see what the criteria are for simple harmonic motion. The acceleration is always in the opposite direction from the displacement. This means the acceleration always slows down the motion and reverses the direction. That is true. It's periodic, back and forth. The acceleration is always in the opposite direction from the displacement. That's also true in this case, right? So the displacement is always going to be positive on this side and negative on this side if we call this x is equal to 0. So wherever the displacement is positive, the acceleration is going to be in this negative direction, accelerating it back to its equilibrium position. And whenever it's negative, the acceleration is going to point in the other way. So on the negative side, acceleration is going to point to the middle. On the positive side, acceleration is going to point to the middle. It is periodic. Acceleration is always opposite delta x. It is an ideal system where it would continue forever, assuming no frictional losses. So no loss due to friction. So far we're looking good. A graph of displacement versus time will result in the trigonometric function sine or cosine. Okay, now here's where we get to somewhere that's a little bit funky. In order for a graph of displacement versus time to result in a trigonometric function sine or cosine, what needs to happen is that the angle that the object starts at needs to be smaller than 15 degrees. That is called the small angle approximation. So delta needs to be, or theta needs to be less than 15 degrees. In the experiment that we did in class, theta could be less than 30 degrees, and that would still be sufficient. But for that reason, for this problem, the object is actually not an SHM. The reason why? Because angle is greater than 15 degrees. This object is dropped off at an angle, presumably 90 degrees, right? So if we look at this angle, in order for it to be in simple harmonic motion, it would have, theta would have to be less than 15. It would have to be dropped off from like a really small angle. But because it's dropped off from this position over here, we know that it is not in fact simple harmonic motion. Yeah, it's a tricky one. All right, this is also a kind of question that you would see on a multiple choice for the AP exam. Draw a free body diagram for the ball for the following positions: the top of the bowl, halfway down the bowl, heading towards equilibrium, at the equilibrium position, halfway up the bowl, heading away, strong force. Okay, cool. So I'm going to draw a sketch of, a bigger sketch of the ball, sorry. what I'll do is I will draw in, well, I'll indicate the force component, the net force with a red pen, with a red marker. I'll indicate the magnitude of the acceleration with the green. No, I'll draw this in with red too. And the velocity will be with purple. Cool. Relative magnitude of the ball bearing's velocity. Oh, this will be fun. Alright, so top of the ball. Call this position A. Halfway down the bowl, heading towards equilibrium. At the equilibrium position, halfway up the bowl, heading away from the equilibrium. Okay. So at each of these positions, what we want to do is indicate which force or force component is providing the restoring force. So why don't we just draw free body diagrams for each of these positions. I'll label this as C. I'll label this as D. Okay. So at this point, there's no normal force, right? The normal force isn't providing any kind of support force. The only force that we have here is going to be gravity. At this 90-degree angle, gravity is pulling straight down. Now, here gravity is also going to be acting straight down, but it is going to have components. It's going to have components parallel and perpendicular to the surface, right? So, and you will also have a normal force. Here you're going to have a normal force and the force of gravity. Here you're going to have a normal force and, similar to this position, force of gravity with parallel and perpendicular components. Now, the restoring force, which force or force component is providing the restoring force? The restoring force in this case is actually whatever force is pointing towards the equilibrium position. So here, the restoring force would be the component of gravity that's actually perpendicular to the parallel to the surface. So in this case, this is a restoring force. In this case, the sum of the normal force and the force of gravity, like the net force, is actually the restoring force here. So gravity is providing the parallel component of gravity is providing the restoring force here, Fg sine theta. And here it's Fg sine theta. Here there's actually no force. It's at the equilibrium position. There's no force providing, there's no restoring force. There's no acceleration. It's at a max velocity. The relative magnitude of the, and this is all based off of the same forces that are acting on a pendulum. So I would refer to this sketch to give you an idea of how to look at a ball bearing that's also on a hill. Okay. The relative magnitude of the acceleration of the ball bearing. So we'll say here, A is max, A mid, A mid, A min. As it gets further away from its equilibrium position, the acceleration will increase. Here it has a lot of acceleration due to gravity. That's pulling it down. Here it has less acceleration due to gravity. Gravity is acting as a restoring force. Here. Relative magnitude of the ball bearing's velocity. V min, V mid, A min, V max. V mid here as well. Acceleration middle, velocity middle. D and B mirroring each other. Sketch energy bar charts for these 4 ball Earth system positions. Include the ball's kinetic energy, gravitational potential energy, and total mechanical energy. Okay. Bar chart should be proportional to itself, but no specific scalar or quantitative values are required. Cool. So let's do A, B, C, and D. Say KE, PE, and TME. Too much energy. Total mechanical energy. Lol. Colorful charts are encouraged. Cool. So let's see. I'm going to draw the total mechanical energy in purple. And one thing we can do straight off the bat is note that at every point, the total mechanical energy is going to be the same, right? I'm going to do total mechanical energy as purple because I'm going to do the other two as red and blue because they combine to make purple. I'm just going to establish that the total mechanical energy is the same at every point. It's just that the kinetic and potential energy are going to change with respect to one another. We'll do kinetic in red, potential as blue. Okay, so at A, all of the energy is potential, right? It's at a minimum velocity. In fact, its velocity is 0 as it's instantaneously on the side at rest over here. At B, like we said in this previous problem, the potential energy is going to be a fourth of the kinetic energy. Potential energy is going to be a fourth of the total energy, and the kinetic energy is going to be 3/4. So why don't we just draw that over here? Potential energy is going to be a fourth. And this can be qualitative. Let me just draw a relative. Kinetic energy is a fourth. At C, it's all kinetic. It's at its max velocity, right? Vmax. So. And at D, the graph is going to be the same as A, right? Or sorry, the same as B. So, because it's at a max or a mid position. Draw that right over there. Cool. On to the next one. All right, we're going to skip 2, A, B, or C, and we're going to go straight to 3. 3 and 4 are light work. Cart with mass m vibrating at the end of a spring has an extra block added to it when its displacement is x is equal to plus a. What should the block's mass be in order to reduce the frequency to half of its initial value? Alright, so we know that frequency is equal to 1 over the period. If we want the frequency to be half, we know that we have to multiply the period by 2. That makes sense. Reducing the frequency by half means it takes twice as long for an object to complete a cycle, and so the period has to be twice as long. It needs to take twice as much time in order to do the same thing. And so we have a formula for a object. TSP is equal to, I forget what it is. Well, let me check. 2 pi is equal 2 pi times the square root of m over k. Cool. 2 pi times the square root of m over k. Square root. Now, we know that we want TSP to be twice as large to get the frequency to be half as large. And so we need to double this. So in order to double TSP, we need to multiply mass by 2. Okay, so then in order to get, or we need to, not, sorry, we don't need to multiply mass by 2, we need to get the whole thing to be multiplied by 2. Now, in order to get the mass to be contribute to doubling the whole thing, this inside of the square root, this mass needs to go up to 4m. Right, this mass needs to go up to 4m. Because that way we can take the square root of the 4 and then pop out that 2. And so to get 2 TSP, the only way of doing this is take the square root of 4m over k. Right, that's the only way we can get a 2 here, by changing just the mass. And so in order to get the mass, we have to get the mass to 4m. The only way to get the mass to 4m is to add 3m onto the mass that exists there already. And so if we have a little cart with mass m, we need to plop 3m on there to make the total mass 4m. When we take the square root of 4m, we get 2m on the outside. So 2 pi is equal to the square root of 2. And
So we end up with a square root of 2 square root m over k.
Hey, how's it going? Yeah, I will absolutely close that window. I can take care of that later.
I gotta make sure.
Oh, yeah, you can close it right now if you want to.
And
Yeah.
I don't need a paper because this way if you forget then,
Yeah, no, sure, absolutely.
are you gonna be here for a little while or?
no, I'm gonna finish recording this video and then head out.
Alright.
Yeah.
'Cause I gotta go up, I already did like Blue House and I gotta keep going.
Yeah.
Sorry. Appreciate it though.
Yeah, no worries.
And have a good night. You didn't
You
get
too.
food?
Yeah, I did. It's good.
Alright.
Alright, so to get for this previous problem, to get the total period to double, we needed to get the mass to go up by 3. We had to add 3m. So the inside of this would be 4m, right? Alright, so a pendulum swings at the period of 2 seconds. The period of the pendulum is equal to 2 pi squared root of L over G. This is light work. We want to get the length of the pendulum. 2p squared is equal to 4 pi squared times L over G. If we're solving for the length of the pendulum, we want L to be equal to 2p squared times G over 4 pi squared. 2p squared is 4 times G over 4 pi squared. 4's cancel out, we have G over pi squared. So the length of the pendulum should be G over pi squared, whatever that is. 9.8 divided by 3.1 squared. Now, if the same pendulum was taken to the moon where the acceleration due to gravity is 1.6 meters per second squared, would the period be greater than, the same as, or less than the pendulum's period on Earth? What a fantastic question. This is very much a question that you're likely to see on the AP exam. Alright, so this is our formula for period. Acceleration due to gravity is 1.6 meters per second squared. So relative to G, it's actually less than G. So it's less than G. The period be greater than, the same as, or less than the pendulum's period on Earth. Alright, so if this goes down, if that acceleration due to gravity goes down, or if this goes down, the entire expression over here increases. So if this denominator goes down, the entire expression increases, and then we have an increase in the period, right? The only other thing that will cause the entire expression to increase is an increase in the numerator. So either an increase in the numerator or a decrease in the denominator will cause the whole expression to go up and the period to go up. So will the period be greater? It'll be greater than. You can justify using algebra. This also makes intuitive sense because if we look at a pendulum, increasing L is obviously going to increase the period, right? Increasing L is going to increase the period because it just takes a longer time for it to go back to its original position. And it's going to go all the way over and all the way back. But also, if we decrease G, what you're saying is that there's going to be less of a restoring force. There's going to be a less magnitude of the force due to gravity that's going to accelerate the object. And so with a smaller G, you're going to have a smaller acceleration, and with a smaller acceleration, you'll have more time required for it to cover, for this pendulum to cover the same amount of distance. Or smaller G, greater
Period. Sorry. Smaller G, greater period. Okay.
That is the video on SHM review problems 1, 3, and 4, as well as the problems from Friday.